Good morning, students. Hope you all are fine and enjoying your online studies. As we have discussed discovery of subatomic particles in previous class, so after the discovery of electrons, protons and neutrons, the next question in front of scientists was that how these subatomic particles are arranged in an atom. So next scientists started thinking about that, and they proposed certain models to explain the structure of atoms. So these earlier models we'll discuss today. The first attempt in explaining the structure of atom was given by J.J. Thomson in 1898, and according to his model, the atom is spherical in shape and it has a radius of approximately 10 raised to the power minus 10 meter. Thomson compared atom as a sphere of positive charge. As you can see in the figure, the whole sphere is made up of positive charge, and the negatively charged electrons are embedded in such a manner to give the most stable arrangement of electrostatic forces. And he compared it with watermelon or plum pudding. As you can see, in a watermelon, the red part can be considered as the sphere of positive charge, and the seeds can be compared as electrons, which are embedded somewhere in the sphere. And also he explained that total magnitude of positive charge is always equal to the negatively charged electrons. Hence, the atom as a whole is neutral. Although he was successful in explaining the neutrality of the atom and the spherical structure of the atom, but still his model was discarded when Rutherford experimented with alpha scattering on a thin gold foil, and he observed the results which were not in the favor of Thomson's model. So at that time, this model was rejected. In 1909, Rutherford with his students performed a series of scattering experiments known as alpha scattering experiments, and in this experiment he bombarded a thin foil of gold with some high energy particles called alpha particles, and these alpha particles are actually doubly charged helium ions having mass 4 unit mass with 2 positive charge. And he produced these alpha particles with the help of a radioactive material placed in a lead cavity, and these alpha particles in the form of a beam, they were passed through few slits and then bombarded on a thin gold foil that he selected for his experiment. And this gold foil was placed in a screen, you can say, and the screen was deposited with some fluorescent material. So whenever alpha particles strike that screen, it produces a glow, and as you can see the glow, they are produced on the screen, and most of the alpha particles were passed through straight without any deflection. For that, he explained that as most of the particles pass through straight, that means atom as a whole is a hollow sphere, and at the center of the atom there is a positive charged nucleus, and whenever alpha particles hit that nucleus, they reverse back. So that is the reason that only a few particles, hardly 1 out of 12,000 particles, reversed back in his experiment, and this experiment disproved Thomson's model of atom. Now, according to Rutherford's model of atom, as we have seen that most of the particles pass through straight without any deflection, so he concluded that most of the part of atom is a hollow sphere, means अंदर से खाली है ज़्यादा हिस्सा atom का. And secondly, very few particles were deflected with small angles, and 1 out of 12,000 deflected through large angle. So that suggested that entire mass and positive charge of the atom is concentrated in a very small portion. It's called nucleus. As you can see in the figure, it's a red colored sphere can be considered as the nucleus, and it's very small as compared to the exact size of the atom. And this discovery of nucleus was a big achievement for Rutherford's model of atom. Next, the electrons. He explained that electrons revolve around the nucleus at a very high speed in circular paths called orbits. And Rutherford compared his model with solar system. As you can see, in solar system, the sun is situated at the center and the planets keep on revolving around the sun. Similarly, here nucleus is situated at the center of the atom and electrons revolve around the nucleus in their fixed orbits, just like planets. And nucleus and electrons are held together with electrostatic force of attraction. So in this way, Rutherford explained the structure of atom. Although Rutherford successfully explained the structure of atom in the form of nucleus, and nucleus was his major achievement of his model, but there was a serious drawback in his model. He could not explain the stability of the atom. For example, if we consider the motion of the planets around sun in solar system, that can easily be explained with the help of classical mechanics using laws of motion, because these theories can easily explain the motion of macroscopic particles, but that classical mechanics cannot be applied on a microscopic particle like electron, which is a charged particle. As we all know that planets are not at all charged bodies. And during that time, Maxwell explained electromagnetic radiation, and he suggested that when a charged particle is moving in a fixed orbit, in a circular orbit around oppositely charged body like nucleus, then it must lose energy in the form of radiation, because in circular orbits the motion will be accelerated, and due to this acceleration it will lose energy in the form of radiation. And when it will lose energy, obviously its speed will be slower and its orbit will become smaller and smaller. And actually it was shown by the calculations also that it will take an electron only 10 raised to the power minus 8 seconds to spiral into the nucleus, and atom would collapse. But actually it is not the case, and as we know that atoms are quite stable. So this was the major major limitation of Rutherford's model, that he could not explain the stability of the atom. Moreover, he could not explain the distribution and energies of the electrons in those orbits. Next, during those years, also developments were taking place on dual nature of electromagnetic radiation. As Maxwell explained the wave nature of electromagnetic radiation, another scientist, Max Planck, was working on the particle nature of radiation. So as radiation's interaction of radiation with matter, it opened the various ways or various new paths in front of the scientists to explain the structure of atom in a different way. And secondly, atomic spectra that could not be explained with the help of Rutherford's model of atom. So these two major developments lead to Bohr's model of atom. Firstly, we'll discuss about these developments. First is wave nature of electromagnetic radiation. Electromagnetic radiation, as you all know, the energy emitted by a source. For example, you can say light we are getting from the sun. So all these electromagnetic radiations have wave nature. This was explained by Maxwell, and it's known as Maxwell's theory of electromagnetic waves or electromagnetic radiation. And Maxwell explained that when an electrically charged particle moves under acceleration, oscillating electrical and magnetic fields are produced. Means whenever energy is radiated, then electrical and magnetic fields are also produced. Hence that is why these radiations are called as electromagnetic radiation. And he explained that both of these fields are perpendicular to each other. As you can see here in the diagram, that magnetic field and electric field, they are perpendicular to each other and also to the direction of the wave propagation. That means the direction in which the wave is propagating, moving, and the direction of magnetic field and direction of electric field, all these three are perpendicular to each other. Means if one is in x direction, then the other one is in y, and the third one would be in z direction. And all electromagnetic radiation or waves travel with the same speed, that is, we can say speed of light 3 multiplied by 10 raised to the power 8 meter per second. And these waves do not require material medium to travel, because you can see that the light from the sun is reaching to earth without any medium in space. So these are the radiations that do not require any material medium to travel. And various types of electromagnetic radiation exist, and that differ in their properties like wavelength, frequencies, etc., and their arrangement in increasing or decreasing order of wavelength and frequencies is called as electromagnetic spectrum. Next, we'll discuss how we can define these electromagnetic waves by using certain properties. As you can see here in the diagram, wave is depicted like this, and these terms by which we can define, first one is frequency. Frequency is the number of waves produced in 1 second, and SI unit of frequency is hertz or per second, and the symbol which is used to represent frequency is nu. Next is wavelength. Wavelength is the linear distance between two consecutive crests or trough. As you can see here in the figure, the linear distance between two upper crust or the lower troughs is called wavelength, and it is represented by lambda, the symbol, and SI unit is meter, or smaller unit centimeter, nanometer can also be used. Next is wave number. Wave number is the number of wavelengths per centimeter, and it is equal to the inverse of wavelength. Actually, if we fix length in centimeters and we count the number of wavelengths in that particular 1 centimeter length, then it is said to be wave number, and its unit is generally centimeter inverse, and it is represented by the symbol nu bar. Nu is the letter which is used to denote frequency with the bar over it, nu bar. And next is amplitude. Amplitude is the height of crest or depth of the trough of a wave. You can see here the height up to which the crest is present, or the depth up to which the trough is present. That maximum distance is called amplitude. And amplitude of a wave decides its intensity. For example, if we are talking about the intensity of light, the brightness of light, it will depend on the amplitude of the light rays, light waves. Now we'll see how these different properties of waves are related to each other. First of all, very important, frequency and wavelength are inversely proportional to each other, and they are related with the velocity of light in this way. C is equal to nu lambda. Here C is the velocity of light, that is fixed, 3 multiplied by 10 raised to the power 8 meter per second. Nu is the frequency and lambda is the wavelength. Next, lambda is related to wave number by this. Lambda is equal to 1 over nu bar. And as lambda is equal to C over nu, so 1 over bar nu is equal to C over nu. Next, as we have discussed that there are varieties of radiation existing in nature, and if these radiations are arranged in increasing order of wavelength or decreasing order of frequency, then the arrangement obtained is called electromagnetic spectrum. As we know that frequency and wavelength are inversely related to each other, hence the radiation which will have highest frequency will have lowest wavelength. For example, gamma rays, this spectrum starts from gamma rays which have highest frequency but lowest wavelength, and gamma rays, after gamma rays there are X-rays, then ultraviolet UV rays, then visible region. Visible region is the region that is the white light that we can see, and IR infrared, then microwave, then radio waves, and at last long radio waves. And you can see here gamma rays have highest frequency ranging from 10 raised to the power 19 to 10 raised to the power 24, but have lowest wavelength, that is ranging from 10 raised to the power minus 16 to 10 raised to the power minus 11, somewhere around. And visible region have wavelength ranging from 400 nanometer to 700 nanometer. And as you can see here, violet color, that is in the sequence Vibgyor, violet color has lowest wavelength, whereas red color has highest wavelength of 700 nanometer. And the radio waves have longest wavelength up to the range of 10 raised to the power 8 meter, and shortest or the lowest frequency. Next, we can have few numericals on the basis of this relationship. First one is yellow light emitted from a sodium lamp has a wavelength of 500 nanometer. What is the frequency and wave number of this light? As we know that wavelength is related with frequency by this formula, nu is equal to C over lambda, and wavelength is given here in nanometer, but we need to solve questions in SI units, so convert it into meter. 580 multiplied by 10 raised to a minus 9 meter, and put the values here. C is fixed here, speed of light in meter per second, and here the lambda is meters, and you will get the answer in per second or hertz. This is the frequency. And wave number, as we know that wave number is inversely or inverse of wavelength, so we can simply write that 1 over 580 multiplied by 10 raised to the power minus 9 is it equal to 1.72 10 raised to the power 6 meter. Similarly, the Vivid Bharati station of air broadcast on a frequency of 1368 kilohertz. Calculate the wavelength of radiation and tell the region to which it belongs. So here we are given with the frequency in kilohertz, and we need to find the wavelength of the radiation. So frequency, first we need to convert it into SI unit, that is hertz, from kilohertz to hertz. So multiply it with 10 raised to the power 3. Then apply the relationship wavelength lambda is equal to C over nu, and C is fixed divided by this frequency, and you will get the answer here in meter. So wavelength is 219.3 meter, and it belongs to radio wave region. Now in this example, we need to calculate wavelength, wave number, and frequency of radiation having time period 2.0 10 raised to the power minus 15 second. And also we need to find the region of spectrum to which this radiation belongs. So let us first of all calculate frequency, as we are given with the time period only, and time period is the total time taken in one cycle or in one wave to complete the time taken. So hence time period is the inverse of frequency, or you can say frequency is equal to 1 over time period, because frequency is the total number of waves in 1 second, and it will be related to time period in this way. And we can find frequency 1 over 2.0 10 raised to a minus 15, and the answer is 5.0 10 raised to a 14 per second. Now from frequency and speed of light, you can say we can calculate wavelength as, and we get the answer as 6.0 10 raised to a minus 7 meter approximate, or in nanometers we can represent it as 600 nanometer. And next is wave number is equal to 1 over lambda. So this is 1.66 10 raised to power 6 meter per meter, or you can also express in centimeter inverse. And now we need to find the region of spectrum to which this radiation belong. As you can see, the frequency is in the range of 10 raised to power 14, and frequency of visible region lies in this region. And also wavelength, you can say 600 nanometer, and this wavelength is, you can see here, it is of orange color radiation, hence this radiation belongs to visible region. So I hope all the things are clear to you all. Thank you. Have a nice day.